Right. So this is problem number 6.2. Right. Yeah. So A is an n by n matrix. Okay. A is an n by n matrix, and this is in MNZ. Okay. Now they are saying that A inverse exists, or maybe I just not write. A inverse is also in this. Okay, it exists and it is also in this. And then we want to show that the determinant of A is either plus or minus. That's the question. Yeah, I mean, it's if and only if. This is what we want to do, because the other direction is quite easy, right? So the other direction is if this is given and if determinant of A is plus minus 1, then that implies that A inverse is also in MNZ. This is trivial, right? Because you know that A inverse is basically adjugate of A by determinant of A, right? And adjugate of A is obviously again having integer coefficients the way it is defined, and this is plus minus 1, so this will also be in. So this is trivial. This direction is trivial, right? So this is obviously in integer coefficients, right? But this is something which we don't know, right? So let's do this direction, right?
What's the question? Like, if A inverse belongs to M and Z, then determinant of A equal to plus minus 1.
Yes. The other direction they are also asking, but that I have explained. I mean, that is easy. That is nothing, right? Yeah. If the determinant is plus minus 1, then A inverse is also having integer coefficients. That is fine. But think about this.
Okay.
Yeah. Yeah. I'm just, okay. You can just forget that part, but let's think about this.
Can you say something like that? As A inverse exists, then we can reduce A to an identity matrix and then find out the determinant that will be either plus 1 or minus 1. Something like that.
Yes, but how do you show that? Yeah. So you're saying you start with A. No, I don't.
We actually, when we find out the inverse matrix of any matrix using the row operations, then we actually change the main matrix to identity matrix, and the identity matrix becomes the A inverse.
Yes.
I mean,
Right.
using same row operations on both sides.
Yes. Right. But
but no, I have the only idea about that. Okay.
Yeah, but does that help you to show the determinant is plus minus 1? That is what I'm concerned about.
If I can reduce the matrix A to an identity matrix, and using that row reduction method and all, so the
Yes, so you are applying row operation. Let's say you apply some row operation and you get here and so on and so on, and finally you get A inverse. But how does it tell me anything about the determinant? That you need to tell me, right? That you need to connect. Right? So you just need to say one thing, that the determinant is a group homomorphism, right? If you say it like that, then it just falls in a second. Problem is over in a second, right? The essence is that when you're inverting a matrix and when you calculate the determinant of the inverse, it is the inverse of the determinant. No? You know this,
Can
right?
you just repeat once?
Yes. So when you calculate the determinant of the inverse, that is inverse of the determinant. This you should prove if you don't have not proved, but you obviously
Yes,
know it
yes,
as a
yes.
fact.
I know.
So if you know this,
Yes,
then
I
there is
know.
nothing in the problem, right? Because this is an integer, right? And so inverse of an integer is an integer, which means that integer is plus minus 1, right?
Yes, yes.
That's it. Yeah. I mean, in general, if you know groups, right?
Yes.
Yeah. So you know groups, and so you just oh no, in groups. Sorry. Okay. Yeah, then that thing is true, but uh, what I want to say is, if you look at GL and Z, which is invertible matrices with integer coefficient, this is the group. Wait, is it a group? No, it is not a group. Sorry. Yeah, it is not a group. So certainly it is not a group. Yeah, then I have to say it in a slightly different way. Yeah, then I say like this. You look at this. This is the ring, correct? This is the ring. Okay? And then you look at the determinant map, right? You look at the determinant map, it goes here. Okay. Now this yeah, but now the problem becomes that this is not a ring homomorphism. Yeah. Yeah, this is not a ring homomorphism, it's a monoid morphism. Yeah, means it only respects the, so what I'm just saying is that this only respects the multiplication. So doesn't respect addition, of course. Only respects the multiplication. So yes, so you see this map only respects multiplication, but then you know that invertible elements go to invertible elements. Do you agree with this?
Yes.
Yeah, anything that respects multiplication, it will do this, right? So just from this formula, you can see that if something is invertible, then its image is also invertible, simply. Yeah. And right, invertible elements should go to invertible elements. This is certainly correct. And so if A is invertible, then it will go to invertible element in Z. But what are the invertible elements of Z? Which is called units, this denotation. Just plus minus 1, right? There's no other invertible element in integers. That also you know, that everybody knows.
Yes, sir.
Right? We are talking about, of course, multiplication. So that's it. Okay, that's all. So you have to always remember this, that invertible elements cannot go to 0. Other things can go to 0, but invertible things should go to something which is invertible. That is because multiplication is being respected. Like you multiply first and then you take determinant. It doesn't matter. You could first take determinant and then multiply. Right? That's what the right hand side does. And also, uh, non-invertible elements, yeah, non-invertible elements can go to, yeah, non-invertible elements can go to invertible elements. That kind of thing can happen. Okay. But invertible elements should go to invertible element. Yeah, in this case, things are more precise, but yeah. So this is the thing. Now, if you think like this, if you think about this as this being a function and this being this talking about units, then the moment you say that, you will know that a that if a goes to a unit, means if a is a unit, this is what it means. So this condition you have to read as not in this complicated way, but just saying that a is a unit in a monoid or ring, but we are only considering multiplication. Monoid is just a ring with only considering a multiplication part. I've defined it last time. That's all. And then it is. Otherwise, you have to just sit and think and apply some thought and rules. Yeah. Yeah. Otherwise, how do you do? You have to think. Probably there will be some ways, but can we do it by Kelly Hamilton? We have done Kelly Hamilton, so maybe that also you can think. If this will not be n, so the characteristic polynomial, we can try to think with all the things you have used, that you have to try to, there should be no inertia in using it. Just, use it on the fly. That's the thing. That's how you grow. Mathematics is a very technical subject, right? It has intuition and everything, but it is technical. So it's always good to use what you have learned to, yeah, to be able to use it later. Otherwise, you simply forget it. So you know that this C naught is the determinant, right? If this is a characteristic polynomial, then C naught is the determinant. That you know. Yeah. So that you should check. So if determinant of, you're looking at this thing, okay, n minus lambda I, this is p lambda, okay, and so this is a characteristic polynomial, so I just use the standard notation, characteristic
Yeah, I
polynomial,
know that.
right? Yeah, p lambda. So then the C naught is the determinant, right? That you understand. Yeah, I mean that you can just see by putting lambda equal to 0, and you can put lambda equal to 0. That's allowed. So C naught is the determinant, and now what is the inverse here? What is the inverse? Inverse is here. This is the inverse. So Kelly Hamilton gives you another expression for the inverse. And so this is the this is the inverse. And we want to prove that this C naught is right. But it's not quite obvious from here, right? Is it obvious from here? The C naught is plus minus 1. All right. So,
What's the inverse here?
oh, this is the inverse. This thing, by definition, right? This is the idea, right? Kelly Hamilton has all this. I've told you, right? Read the applications of Kelly Hamilton, read the Wikipedia page of Kelly Hamilton, or read it from any book. And you see these are all standard applications of Kelly Hamilton. There are many like this. This is, you just read and you see there are many applications. So Kelly Hamilton is a very big, is very important theorem. This thing, but from here, can you prove that C naught is plus minus 1? That is not clear. Right? It's good if it, I mean, it has to be, if it is plus minus 1, then it is good. Then the inverse is integer coefficient. That is clear. So you can avoid the adjugate formula. The converse of this theorem you can prove, right? Means if C naught was plus minus 1, then the inverse will just become this, which is clearly having integer coefficient. But our question is that the thing is, this is given to be integer. This is given to have integer coefficients. This is a matrix, remember? And then we want to prove that C naught is plus minus 1. That is not clear from here. Good. So this, yeah, I don't know that. This I don't know. I don't know how to do it from here. Maybe there's not enough information. Okay, so let's move on. Let's do one more quickly. We talked a lot in this. Yeah, let's do this M1 star. It's the star question. Is equal to CA. Right. So this is like a block formula for determinant. This is a miscellaneous question. Block formula for determinants. Right? So A is 2n by 2n. ABCD. These are all square. Okay. So these are square matrices. Okay. So it's a matrix of matrices. And again, this problem is to make the calculations easier. And if you see it like that, this determinant is just mimicking the usual determinant rule. It's equal to determinant of this matrix AD minus B. You first calculate the determinant here and then you calculate the determinant of that. Okay. But of course, this is not always true. You need the commutativity. I think I'm writing something wrong. No, it's fine. Yeah. You need AC equal to CA. Yeah. AC equal to CA. This is given. Under this, we have to prove that this happens.
AC equal to C is this, I mean, every time we need it.
Yeah, this is given. So you just assume it. Okay. Assume that this is given. Then you prove this. Okay. Yeah. Every time you need it means what? No, I don't know. Sometimes it may
I
happen that
mean,
AC, no.
if AC is not equal to CA, then the determinant formula
With
will
this
be
formula will
existed.
not hold. Yeah. Then in general, this will not hold.
Not hold.
No,
Okay.
yeah. Because why should this hold? Right? This is a very strange formula, right? Because these are not numbers, right? Determinant formula that you know is for
No.
numbers. Yeah. So hey, so first a priori it should not hold. And they are actually asking to give counter example also. So it's not always. But sometimes it may happen that this is not holding and still it holds. But that cannot be guaranteed. There will be counter example. But if this holds, then certainly it will be. If this holds, then certainly you will. Let's think about this. I don't know how to do this right away. It's a star question.
Okay, I will give it a try at home.
You will do it at home. Okay. Okay. And try it. Right. So you can think about two ways. Okay, maybe. So you can think about that formula which is there for determinant, right? In terms of permutation. So you see, right? I mean, it's like if you think of these as n entries like this and then n entries, right? So it's like what? You pick something from, so if you move row wise and from every column you pick one number, right? So you pick some things from these from the first n rows. When you traverse, you pick one entry from every column, and then the last n rows you pick. So this is basically considering those cases in which you pick from here and then here and then here and here. And the ones in which it is mixed, in which you pick in a mixed way, those somehow, those terms which you get, those will somehow cancel out because of this condition. That is what they're saying. Okay. And that's what one way. The other way is to, but that probably you don't know. This is a, you have to show that this is an alternating multilinear function. If you put x, y, z, w. Just let me think for a minute. Is it? So if I want to take one row, yeah, this is, you can show that, and then it will be done. Yeah, that's a good way, I think. But yeah, okay, try it. But yeah, do it. And that formula is still very useful also in many problems. Okay, then you can maybe try it in the next 10 minutes also. Right, and then maybe we can do group actions. Some group actions were discussed in that workshop also, right? They were doing group actions, but obviously,
Yeah, but
they, they
our
did it.
syllabus has given something different. I mean,
Yeah. It
whatever
will
is
be.
done in our class, they just give those type of questions.
Okay. So we'll see. It will be easier.